All right, students, hitting up a math connections portion here. Math connections is 1 through 5 all and 10 through 20 evens only. Okay, so only the evens on 10 through 20. So let's take a look. Uh yeah, so I want 1 through, what did I say? 1 through 5 all. Okay, so 1 through 5 would be explain why the product of any three consecutive numbers is divisible by 6, why I need 4. All right, so why don't here's the thing, right? We're going to do the Civa Veritasenes in class. I wouldn't worry too much about that one if you're trying to work ahead. But link up to what we did in class. We're going to be doing kind of a coloring activity. And then 4, without multiplying, show that none of the primes less than or equal to 19 divides this. Okay, that's using our theorems from 4-1. So again, don't need us here for that. And the numbers 2, 3, 5, 7, 11, 13 are not factors at 353. Explain why it's possible to conclude this is prime without checking anything else. This utilizes what we're doing with the Civa Veritasenes and also with the prime squared. So I feel like what we've done to this point, you might be able to get that one on your own. Let's check and see. Let me get a little white space. Why don't let me give you kind of a nudge in the right direction on one of these. So, okay, so here we go. So if I was you and I said, okay, now I need 3 consecutive whole numbers, right? And the product of any 3 consecutive whole numbers must be divisible by 6. Okay, now that makes sense, right? So it doesn't really matter what the first one, I need 3 consecutive whole numbers. So just to start, let's do an example with some numbers. Let me pick the number 7, I guess, right? 7, and we'll multiply 7 times 8 times 9. Okay, so I'm going to multiply those 3 numbers just to make sure we understand what it's doing here. 7 times 8 times 9 gives me the number 504. So that's a pretty big number. And when I divide by 6, I get 84. 504 divided by 6 is equal to 84. So that actually checks out. So it is. I found 3 numbers, 3 consecutive numbers. I multiply them, and the result is divisible by 6. Now remember, that's just one example, though. Examples do not guarantee it happens all the time. And this does say any 3 consecutive whole numbers. So what we want to do is we need a number, and then the next number after it would be like the number 8, which would be 7 plus 1. The number after this would be 9, which is 7 plus 2. So we want to think of a general number, whatever you start with here. So let's call it n. It's just for number, right? And then the next number would be n plus 1, right? And the next number would be n plus 2. Okay, so there we go. Okay, so let's see here. In order to be divisible by 6, remember checking for 6, we need it to be divisible by 2 and 3. Okay. So if it's divisible by 2 and by 3. All right, so we could do the test for 2. The test for 2 is we need it to be an even number. So we need the last digit to be divisible by 2. But we could also just say it needs to be an even number. So the question is right here, I don't know whether I'm starting with an even number or an odd number. So this could be even or odd, right? But if it's even, if it is even, then when I multiply it by a bunch of other numbers, it has to be a multiple of 2, because if it's even, it already is a multiple of 2. So if it's even, we're good, and the whole number, whatever I multiply by, will be divisible by 2. But that didn't happen for us here. Notice the first number we chose was a 7. Okay, so let's just say it's odd. What happens to an odd number when you add 1 to it, right? If you have an odd number, you add 1, it becomes an even number. So if the first one was odd, the next one is even, and the last one is odd. But anytime you do multiplication with one even number, the whole thing becomes even. Remember, even numbers are closed under multiplication. All right, love it. So that takes care of the 2, so definitely divisible by 2. Now let's check divisibility by 3, which means I need all the digits added up, okay? And whatever the digits are. So whatever number I have here, I have +1, +2. So if you add these digits up, in a sense, you're going to have like the number itself, right? Plus n plus 1 plus n plus 2. Okay. So if you think about it here, what you're going to end up with is the number plus the number plus the number. That's 3n's plus, and then bring the other pieces down here. 1 plus 2 is 3. And guess what happens when you add those together, right? Yeah, you end up with 3 times n plus 1. So this is not the product. That doesn't tell me the number over here, 504, but it tells me is it will be 3 times n plus 1 as I'm doing it. So I have that really nice property here that I will get a multiple of 3 guaranteed. Now, there's another way to look at it, though. So let me just scribble that out, because again, some of you are like, how would I have gotten that one? Okay. Let's say we take a number and our number n, and we say it's not divisible by 3. Okay, it's not divisible by 3. Got it. So that means there must be some kind of remainder. So let's say our number is a multiple of 3, but it has to have a remainder. So I'll say +1. I'm like, ha, ha, ha. I got sneaky there. I added 1 to a multiple of 3, so it's not divisible by 3. Perfect. Now we go to the next number, though, and the next number, we add 1 to it. Aha, that's 3 times a number plus 2. Still not divisible by 3, right? Now we come to the last number, which is n plus 2. So if I add 2 to what I started with, guess what I end up with? 3a plus 3. And what I end up with here, this 3 divides both of those. So this is really 3 times a plus 1. And who cares what these other things are? Because now you end up with 3 as one of the factors, because these are all multiplied. And if 3 is one of the factors, 3 does divide the entire number. So boom, shakalaka, you're good to go. All right. So there it is. Any 3 consecutive numbers, you multiply them together, guarantee it's divisible by 6. Guarantee. Okay. You could do a different one. They could do one that says the sum of any 3 numbers must also be divisible by 3. That's a good one, but that's for the sum. This one was product, so I'm going to stick with just what it said here. All right. Love it, love it, love it, love it. Okay, let's see here. 1 through 5. Then I picked a few other ones, which were, I think, 10 through, is that what I said? 10 through 20 evens only. So 10, explain why each of the following numbers is composite. I mean, the first one, again, don't read too much into these. It's a product of primes. A composite number has more than 2 factors. So that's all you need to say. Has more than 2 factors. Is more than just 1 times itself, right? So if you can find a factor, a prime number that divides into that number, and there's more left over, then it is not a prime number itself. So that's how you can do that. And they do mention 10 factorial. That's that symbol, the exclamation point. It's more than just a very excited 10. 10 factorial is a way of writing 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You multiply those all out. And so they're now saying take that number. And again, I would recommend that you don't actually multiply this all the way out, because you're trying to see if you can tell someone why it has to be composite. Let's look forward. 10, there's 12. Student asked their teacher how old the children were. The teacher said, I have 3 kids. The product of their ages is 72, and the sum of their ages is the number of this classroom. Okay, that sounds sneaky. It sounds like a math teacher would do something like that, right? The teacher asked for the door to be open to verify the room number. Okay, so they went outside, they look at the room number, got it. And then Carly says she needs more information to solve the problem. The teacher said, my oldest child is good at math. And that doesn't seem like much of a clue, but then Carly's able to announce it. So if you are working through this problem, Feel free to pause or stop the video if you want to do it all on your own. I'm simply going to give a little bit of a nudge, and a nudge in the right direction. You know she has 3 kids, and the product of the ages is 72. What does that tell you? You need 3 numbers, an A, a B, and a C, and they all have to multiply to the number 72, right? So is it possible that she could have something like this? 1 times 1 times 72? It's possible, right? But if you think about that, a 72-year-old child, and then you have 2 new twins. And my best to assume that when we're talking about I have 3 children, we're talking about 3 biological children. So here we go. 1 times 1 times 72 seems a little bit far-fetched. 1 times 2 times 36, again, maybe, right? 1 times 3 times 24, again, I guess it's possible. I mean, that would, if you go ask your parents if they would have wanted to have a child and then 21 years later have a couple more, maybe that's not at the top of their list. Let's see here. 1 times 4. Let's see here. Does 4 go into 72? Yes, it does. Was it 18? 18 times 4. Yeah, 40 plus 32, 72. Okay, so 1 times, let me do a 6 here. 6 times 12. 1 times 8 times 9. Okay, so I'm listing all of these possibilities starting with a 1-year-old. Okay. And then what I'd have to do is, of course, this is the product. The sum would have to be listed. So 72 plus 1 plus 1, the sum would be 74. 36 plus 2 is 38. 39 would be the sum. So these are the sums. And so I just kind of list all of these in my way of kind of getting all the information possible. 24 plus 4 is 28. Dot, 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 dot. Okay. Then, of course, this is all just with one child being 2 years old. So if I do 2, notice I don't really have 72 anymore. I have 2 times 36. Now I need numbers that multiply to 36. Okay. Now notice I can't do 1 again because 2 times 1 times 36 I already have. So I really don't want to do that again. Okay. So I want to make sure I'm like, let's not do things that we already have. So I'm going to do 2 times only another multiple of 36 that, or another factor of 36 that is at least this age. So 2 times 2 times 18 could work. That could work. So 2 2-year-olds and an 18-year-old, that's possible. Let's see here. 2 times, I need 36. So 3 times 12, that's possible. 2 times 4, 2 times 4 times 9. Okay. And that's it for the 2s, right? And then could I have a 3-year-old as the youngest? Maybe. So if I had a 3-year-old, that would be 3 times 24. Now again, I can't have something I've already repeated. So 3 times 1 times 24, that's already listed, right? 3 times 2 times 12, I've already got that one. So I need something that's in like the 3 times 3 level. That would be 9. And 9 times 8 would work. Okay. And then I need 3 times 24. So 3 times 4 times 6. That could work. Okay. Okay. So next up would be 4s. So if I did a 4, it would be 4 times, is that 18? So I need things that multiply by 18. So 4 times, was it 2? So 18 would be 1 times 18, 2 times 9, and 3 times 6. So if you look at these, all of them have a factor that I've already listed. So 4 is out. So really this lists all of them. Okay. Now, the clue to this, and I'm going to give you, this is my hint. This part here kind of describes how to get the list. You have to find the rest of the sums. So the kids go out and they open the door to the room and they go, Now, just understand, if the door was opened and the room number was 74, this is the only one that's 74, they would know how old her kids were. They would know. So the only time that Carly's going to say, I need more information, is if maybe when you make this list of sums, maybe there are two sums that end up being the same. And then that's when the teacher said, aha, next bit of information, right? And that clue says my oldest child is good at math. And that is a big clue. That means she must have had an oldest child, right? So that's kind of the piece that you might have there. Let's see here. Oh my gosh, I missed one in here. Sorry about that. 2 times 6 times 6. I don't know why I didn't go up for 36 to 6 times 6. Oh, crazy kids. All right, so then there we go. So anyway, there's a lot of different factors, and I just happened to miss one. I don't know why. 2 times 1 times 2 times 3 times 4 times 6. I should have done that. Let's see. Do I need a 3 times 6? If I do 3 times 6, it would be times 4, and I've already got it. Okay. So I just missed that one. Okay. 20. There's the little clue on that one. Sometimes these puzzles, they feel like, hey, I feel like I don't know how to do that one all the way, but there you go. And then let's see here. 14 to test divisibility by 12. One student checked 3 and 4. Another student checked 2 and 6. Are both students using a correct approach to divisibility by 12? Why or why not? This is one I'm going to leave for you because I've covered this a couple times. If they have a common factor, maybe something doesn't work, but you should be able to come up with a counter example for a student who is doing this. Mary says her factor tree for 72 begins with a 3 and 24. So her prime factors will be different from Larry's because he's going to start with an 8 and a 9. If you haven't done something like this with kids, sometimes they think because we started differently, the end result will be different. What are you going to tell Mary about this, and how can you clarify it? And I hope that at some point in time you do mention the fundamental theorem of arithmetic, which is kind of a big deal. Let's see here. Lastly, Joe says every odd number greater than 3 can be written as the sum of 2 primes. Oh, interesting. Okay. Okay. To convince the class, he wrote 7 equals 2 plus 5. That makes sense. 2 primes. 5 equals 2 plus 3. 9 equals 7 plus 2. So again, it's the sum of 2 primes. Okay. How would you respond? So make sure you answer. Is Joe on the right track? Is it correct? Can he just use examples to prove something, to convince people of something? Is this a good approach? What might you do different? And if he's incorrect, make sure that you have a way of showing him that he is incorrect. And lastly, a student claims the sum of 2 primes is never a prime number. This is one I think in a prior edition that they had written down as, look, 5 plus 7, those are 2 primes, and I get 12, right? 5 plus 11, those are 2 primes, and I get 16. 7 plus 11, those are 2 primes, and I get 18. And the result of those is never a prime number. So therefore, the sum of 2 primes is never a prime number. They want to generalize what they're seeing. Probably the student is doing the same thing because they just are checking things. How would you respond? I think for this one, I didn't have any extra, did I? Oh, group number 1. That's right, group work number 1. So group work number 1 is up here. This is a fantastic question. And we've got 100 people waiting in line for a baseball spring training game. So I'm going to open up Excel. And the reason I'm opening up Excel is that I'd like to get a kind of a way of visualizing this. And so I'm going to stop sharing for just a second while Excel opens. You could do this by making a grid and then just writing the numbers in the grid. Okay, that's totally fine too. What did last time I taught the class, somebody said they did coins. You could do it with coins too. And here's how you do it. Well, you'd need 100 coins, or 100 somethings that you can identify as being kind of up or down, like a hat on or a hat off. Okay, so totally up to you what you choose to use for this. I'm going to open up Excel. Okay, and all I'm going to do in Excel is make a quick grid so that I could print all the numbers. Okay, and let me go ahead and I will share my screen on that. So in case if you use Excel or something like this, you can do the same thing. So here's what I'm going to do. I'm going to start with the number 1. Right next to it, I type an equal sign, and then I say, click on the cell before it and type +1. And what that does is it takes whatever number was there and adds 1. And then what you can do is you can click in the bottom corner and say, just keep doing that for a while. And it will just kind of create the 1 through 10. Personally, I like these centered. So I click centered. Now here comes the fun part. I need to go up to 100. I do not want to be here all day. So I'm going to say equals the prior number from the other row +1. So now I have the number 11. But the number above it was linked to the cell to the left. So if I drag everything here down 1, watch what happens. It automatically does everything I need. And then I can highlight this row below it and drag down in that little box, and I can get all the way up to 100. So let me delete these. Okay. Now this would allow me to print a grid. Okay. So what I'm going to do is this. Let's go back and read the question. Let me see here. I guess let me just share the whole screen. So if I minimize, you can see everything. Okay, here we go. There's my Excel. Here's the group work. There's 100 people waiting in line for a baseball spring training game. The manager gives each person a free hat and then asks them to participate in a contest where the people with their hats on at the end get a free admission to the game. Okay, sounds cool. He asks the first person in line and then every person after that to put on their hat. Okay, and asks the second person in line and then every other person after that. Okay, so every second person. Okay. So let's take a look. So basically he says, okay, first person, everybody puts on their hats. So basically everybody at this point is going to have their hats on. So I can highlight them. If you have coins, if you're going to do this with coins, basically say, okay, everybody puts their hat on, which means all the coins are heads up. Now you need to have numbered places here. Okay, it's going to be important. Here's why. Then the manager says, now I'm going to tell person number 2 to take their hat back off. And I'm going to tell every other person to take their hat off as well. And that would mean every other person would be all of the even numbers would also kind of take all their hats off. So all these people now have their hats off. Notice who does have their hat on is still kind of all the odd numbers. Okay. Let's go back and keep going with the clue. Then every third person changed their status. Every third person changed their status. Okay, so every third person changes their status. So person number 3 had their hat on, they take it off. Person number 6 had their hat off, they put it back on, right? Person number 9, they would take theirs off. This is why with coins, it's actually not too bad because you're just kind of moving 1, 2, 3, flip, 1, 2, 3, flip. 9, person number 12 would put their hat back on, right? 13, 14, 15 would take their hat off. So I could go through and do this for all of these people. I'm gonna 21 would take their hat off. Okay. So basically, if you look at all the 3s, everything changes. So from 21, so 21, if I add 30, 51, and 81, those would take their hats off. Okay. In this column, 12 put their hat on, so 42, 72 would put their hats back on. So you can kind of go through the columns if you wanted to. I'm just kind of shortcutting a little bit here. 15 is out, this one's out, this one's out, so they would take their hats off. So what you see is a whole bunch of people have their hats on and a whole bunch of people have their hats off, right? 12 is there, so 24 would put their hat on. That means 54 and 84 would put their hats back on. So I'm not going to do all of them, but you can kind of see what's going on there. Okay, then the fourth person, right, changes their status. Okay, so person 4 puts their hat on. That means all multiples of that. Person 8 would also then put their hat on. Person 12 would take their hat back off, right? Person 16 put their hat back on, and so on and so forth. That's person 4. Person 5 changes their status, so their hat comes off. All multiples of 5 change their status. Okay. and you keep going the whole way. And so you do this for the fourth, the sixth. Now, once you get past somebody, once you get up to it, and it's like the person number 15, right? All multiples of 15, you don't have to worry about the ones before it. So what you get is you start to see some pattern here as to who's going to win. So you can kind of tell right here, person number 1, they're getting free admission because no one's going to come back and flip their hat again. Okay. So anyway, try this. Try this with coins. Again, I think that's kind of a good one because you have heads and tails. And just go through and say, put the coins next to the numbers and just flip them over as you go. Then every third, flip, flip, flip. Then every, and so forth. Yeah. So that would be kind of a fun way to do it. Again, multiples of 4, you'd flip. Multiples of 5, you'd flip. Multiples of 6. And as you get higher and higher, like multiples of 15, there's not really that many coins to flip over anymore, right? It's 15, 30, 45, 60, 75, and 90. And that's it. So there's only like 4 coins to flip over. And as you keep getting higher and higher, you'll start to realize there really isn't that many coins to flip over anymore. If you did 41, so 41 takes their hat off. 41 plus 41 would be 82. The next number would be 123. So it's not even on the list. So once you get through the first couple and you kind of get up into the tens, you start to realize it actually goes pretty quick after that. It's a little slow at the beginning, but it's pretty quick after that. Okay. Your goal is to see kind of who's going to get free admission. Maybe you can find a nice little pattern. And believe me, there is a really nice pattern to this one. So anyway, hope that helps out with the MCs. Take care. I'll see you soon. Off you go.